Introduce our next plenary speaker, Professor Harry Atwater from Caltech. Harry, please.
Okay, thank you, Nader, and thank you, Saeed, and the organizing committee for the opportunity to speak here. So I'd like to talk today about the ways in which we can use electrical tuning of nanophotonic materials to modify the complex index. We've seen already some beautiful examples in the previous talk and then in some of the presentations throughout the week. And the way in which we can actually tune the complex, the permittivity and the complex index of materials in sub-wavelength elements that essentially act as antennas, and antennas in arrays which form the building blocks for metasurfaces. And I'll show examples today from a number of classes of materials. And we'll first of all start with metals. You may wonder whether or not we can actually tune the properties of metals, and we'll see what the opportunities are there. And then we'll also look at some materials where we change the carrier density to achieve new degrees of freedom in tuning the properties of materials, including new materials such as graphene and topological insulating materials in the narrow bandgap semiconductors, as well as conducting oxides. And we'll see a couple of examples, a number of examples in which electrostatic potentials change the complex indices of materials, but also several in which the changes in the complex index in resonantly excited nanostructures actually induce electrostatic potentials, sort of the situation running backwards. And finally, I'll discuss the opportunities for control not only of the amplitude of absorption and transmission, but also the phase in antenna arrays. And their work itself is done by a talented group of students and postdocs working at Caltech. And I will note some of the speakers, some of whom will be speaking here in this conference as we go along. And so, as we know, in the last few years, the field of metamaterials has gone into the two-dimensional world of metasurfaces, and metasurfaces essentially comprise arrays of antennas whose complex index can be varied by tuning the geometrical properties of sub-wavelength resonators, and they interact sufficiently strongly with light, and this is a critical point, that we can make two-dimensional arrays and obtain very strong scattering properties, changes in the complex index in just a printed two-dimensional array. And this has been a real boon to the field of optical metamaterials because, of course, the enormous challenges in building three-dimensional structures of sub-wavelength materials in the optical and infrared. And this has led to the ability to make so-called reflect arrays that serve as analogs to structures that were earlier, of course, developed in the RF frequency world, but also to use sub-wavelength arrays to enable holograms, negative refraction in two-dimensional arrays of antennas, and to change the directivity, beaming radiation within the plane. And of course, this has also really exploded into a field of its own. We saw some nice results from Federico on Monday, including the ability to form arrays and tune the effective refractive index properties of metasurface arrays to enable a flat object to serve as a focusing lens in the infrared and the visible, to control the polarization and orbital angular momentum properties of light through optical vortex generation, and to create a ever-expanding variety of structures, both in metallic and dielectric antennas, which in ensembles form metasurfaces. An important thing to note about all of the applications that I just described is that all of these have constitutive optical properties, phase and amplitude response, that were fixed at the time of fabrication. So typically these are made by nanofabrication, and in metallic or dielectric antenna arrays, the response that you see and the rich variety of behaviors that are manifest here are all fixed at the time of fabrication. And so that means that we're able to achieve sort of snapshots of still holograms and images and focused beams but we'd like to move from the world of the essentially daguerreotype and still photograph to the film and television world of metamaterials and metasurfaces. And so there's been now an effort to explore the properties of metasurfaces that have dynamically tunable complex optical properties, and through the use of changes in the carrier density in graphene. You've seen a number of examples of this in the previous talk and then also in John Pendry's talk, and I'll amplify on this a little bit today, as well as changing the geometrical properties of metamaterials by changing the properties of unit cells and the periodicity of the unit cells, by coupling to very anisotropic media like liquid crystals, and by changing the carrier density using field effect tuning in conducting oxides. And so underlying this is the notion that within metasurface and metamaterials, the fundamental object that essentially we assemble into arrays are nanoantennas. And this is a field that's now more than 10 years old. And here you can see some pioneering results from the lab of Dieter Pohl that showed the first example in which a split dipole antenna at optical frequencies served to convert wavelength scale, the wavelength of light to focus light down to deep subwavelength dimensions. And this, I think this field was really enabled also by this iconic image that was developed by Jean-Jacques Graffet that notes the analogy between an RF antenna that couples waves in free space to a load of deep subwavelength dimensions. And so we can couple scatterers and emitters that are deep, much smaller than the wavelength, to the optical wavelength transformed through the interaction with an antenna. And so so optical antennas have been coupled to emitters, for example, active quantum dot emitters and lasers, to achieve control of the directivity of subwavelength emitters as well. And so if we were to ask to be able to achieve complete control of the properties of light, what we would ask an antenna to do would be to control the wave vector, the wavelength, the scattered amplitude or emitted amplitude, but also the phase and polarization in either scattering, absorption, luminescence, or thermal emission. And we'd really like to be able to do all of this as a function of time. And if we have that opportunity, and so we'll see how far we can get in today's discussion, and we'll see that many of these are now achievable by electrostatic potential control. And if we're able to do that, we could see a number of interesting applications that might be made possible, in which the current ability to create, for example, holograms from static arrays of antennas in metasurfaces by controlling the phase amplitude properties to enable things like holographic display and, for example, light detection and ranging analogous to radar at RF frequencies, which has a number of very interesting applications in the optical and infrared regime. So to think about how we can change the properties of materials, let's think about, first of all, the fundamental constitutive property, which is the dielectric permittivity. And we'll just simply make a simple Drude model and note, looking at the properties of the permittivity as a function of frequency. And we can see that basically the zero permittivity basically divides the domain of positive permittivity or dielectric materials and negative permittivity or plasmonic materials. And so at a typical carrier density of a, say, degenerately doped semiconductor, we can see that across the infrared and visible range, we have a permittivity that's positive and constant, essentially a dielectric material. And that accords with our everyday experience with the complex index of lightly doped semiconductors. But of course, even in the far infrared, such materials have sufficient conductivity to exhibit negative permittivity and be plasmonic. But So we can see that in this regime, essentially as we modulate the carrier density, there's very little change in the permittivity. For example, if I change the carrier density to 10 to the 19, either by doping or field effect modulation to change the local carrier density, you can see that in the infrared regime, in the mid to far infrared, we see a significant change, but in the near infrared and optical range, we still see hardly any effect. So to really have a strong effect, we need to go to higher carrier densities characteristic of semi-metallic materials, things that lie intermediate between dielectric and metallic materials. And finally, if we go into the domain of true metals, we see that the permittivity becomes negative at optical frequencies, and that's, in fact, manifestly responsible for the plasmonic response of metals and their beautiful color and phase properties. So this is really now tells us the range of carrier densities that we'd like to be able to access to have a strong effect on the permittivity and the phase and amplitude response of materials. So the simplest kind of optical antenna that we could make would be just a metal nanoparticle. And if we think about what are the opportunities for tuning the extinction of a metal nanoparticle? So if we take the same Drude picture for the permittivity and we look at the extinction, we can see that if we were able to change the carrier density in this metallic nanoparticle by a few percent, we could tune slightly the resonant frequency and the extinction of a metal nanoparticle, just from very simple considerations. And in fact, we can do this, for example, by putting metal nanoparticles in an electrochemical cell. And in order to do this, because of course the intrinsic carrier density of the metal is very high, in this case in the 10 to the 22 range, we have to be able to go to an environment that applies a very large electrostatic charge. And to do this, we use an ionic liquid in an electrochemical cell. And in so doing, we can see that with a few volts applied bias, tuned here from about plus 2 volts to minus 2 volts, we can actually see tunable extinction of material in the and a change in the resonant frequency and also the line width. And so what we see, if we look carefully at this and we look at the change in extinction coefficient, is that we see a red shift for a positive applied bias and a blue shift in the extinction for a negative applied bias. And this is in accord with our simple Drude picture, something that occurs for a change in charge density of a few percent. So indeed, even metals are electrostatically tunable if we apply a large enough potential. But to really understand this, we have to now modify the complex dielectric function of a metal and take incorporating potential dependent terms that account for the resonant frequency as we change the charge density and polarizability. But also, we find that this changes not only the resonant frequency, but also the resonant line width. And this is easy to understand because in a metallic particle, as we add and subtract charge, that charge from simple electrostatic energy minimization considerations is distributed in a thin shell interacting with the interface of the material. And as we polarize that charge, then of course that excess charge disproportionately engages in scattering with the surfaces and interfaces of the particle, and we see then that that produces changes in the line width. So indeed we can see that metals are tunable, and so we can see that by applying electrostatic potential we can tune the properties of metals. What about the opposite? If we were to resonantly excite a metal particle with a narrowband excitation source like a tunable laser source, on the blue side of the resonance frequency for a neutral metal particle, what we can see actually is that that particle, from free energy considerations, can minimize its total free energy by adopting a non-neutral configuration. The way to understand this is that the increase in extinction leads to a change in the entropy and the entropic heat contribution to the free energy. And in fact, so the particle will adopt a charge density different from its neutral particle, different from its neutrality under uniform or broadband excitation. And so if we excite with a narrowband excitation source on the blue side of the resonance, we see a blue shift and a negative charge density, and exciting with the narrowband excitation on the red side, we see a red shift. And indeed, when we map out the expected changes in potential, we see a sort of sigmoidal type change in potential with resonant excitation, which has a zero neutral particle when excited at the resonance frequency, and which a potential which is induced that we call the plasmoelectric potential that changes from positive to negative as we scan a tunable laser source, say, through the resonance. And indeed, as we use, for example, electrostatic force microscopy, Kelvin probe microscopy, we can see that this sigmoidal trend is manifest. And this is consistent with this free energy driven change in the charge density, and is distinctly different from the thermoelectric response, which wouldn't be expected to have this sign changing sigmoidal response. And indeed, not only metal nanoparticles, but other subwavelength metallic motifs like plasmonic Hall arrays that exhibit optical resonances whose periodicity is or whose frequency is tunable by changing the periodicity, also exhibit this sigmoidal change in potential, which can be relatively large, as high as some number of tens of millivolts. But of course, to change the complex permittivity of materials, we need to go to lower carrier densities, where by applying an electrostatic potential, we can change the carrier density by a much larger fraction than the few percent that we're able to achieve in metals. And of course, that leads us to consider the possibility of changes in the permittivity of graphene. And graphene, of course, has inspired a lot of attention and excitement because of the extremely high plasmon mode confinement. We see that the confinement factors as large as 100 are achievable, meaning that the plasmon wavelength in graphene can be a 1/100th of the wavelength in free space. And it's the wave vector and wavelength are tunable by changing the carrier density, which can be electrostatically tuned, changing the Fermi level in graphene relative to its neutral condition at the Dirac point. And this has been this confinement property was first predicted by Marin Sulicic and co-workers, and was beautifully confirmed in a series of apertureless, scanning apertureless microscopy experiments from the group of Coppens and also Dmitry Bozov, showing this nanoscale plasmon wavelength even at far infrared free space excitation wavelengths. And if we think about graphene as a metasurface material, it has some very interesting properties. We can make nanoscale resonators in extremely short wavelength. But graphene has, and graphene as an extreme material, it has very high optical absorption per unit thickness, but of course it's only one atomic layer thick. And its absorption, which you can obtain from fundamental considerations, essentially from the extreme two-dimensionality of the density of states, emerges this simple expression for the absorption in terms of fundamental natural constants, pi times the fine structure constant. If you multiply pi times 1/137, you get an absorption of 2.3%. So graphene is a very weak absorber, and we can see this in single pass transmission experiments. So in order to achieve higher absorption in graphene, we can produce resonant structures. And we can make resonant structures by patterning graphene into thin ribbon resonators, which when excited by a transverse polarized normally incident wave, we can excite the lowest order electric dipole mode. In this case, we have a graphene sheet patterned using subwavelength few nanometer scale nanoresonators in a large area ensemble. And we can, all of these graphene ribbons, which form an ensemble of resonators, can be tuned in their carrier density by a common electrostatic gate, by backgating with a doped silicon substrate. And I'll note that draw your attention to the talk later this afternoon by Victor Brar, who will describe in more detail these results. And so the properties of these resonators are very interesting. They allow us to tune what we see as we change the carrier density from Fermi level positions near the Dirac point to negative potentials that lead to hole doping of graphene. We see the emergence of a electric dipole resonance, a graphene plasmon resonance. And as the carrier density changes, of course, the resonant frequency shifts to higher energies. And we can see also if we change the width of our electric dipole resonator, we can induce at a constant carrier density a change in resonant frequency here over quite a wide range, even above this energy, which is the optical phonon energy in graphene. And the electric dipole modes are depicted here in a simple full wave simulation. And you can see they're extremely confined within a few nanometers of the graphene ribbons themselves. And that tight mode confinement means that the graphene ribbon can couple extremely strongly to its environment. So for example, if we put these graphene nanoresonators in contact with a monolayer film of boron nitride, we can see extremely strong coupling of the graphene plasmon to the phonon polariton that is excited in monolayer boron nitride. And the hybridization of the phonon polariton with the plasmon leads to a hybridized interaction as we change the carrier density in graphene and we tune the graphene plasmon resonance. It crosses the phonon polariton line in boron nitride. This is shown here for a bulk boron nitride, showing the position of the phonon polariton peak. And you can see here there's an apparent anti-crossing behavior, a splitting of the graphene plasmon resonance as it hybridizes with the phonon polariton. And if we work with resonators, electric dipole resonators of different sizes, we can actually map out the entire dispersion relations here and see this nice anti-crossing here manifest as a coupling between the phonon polariton and the graphene plasmon. To further increase the absorption and really achieve very large absorptions in graphene, we want to go to a resonant sort of structure that was first noted by Salisbury in the microwave literature, who essentially was interested in the problem of making very high impedance surfaces. And what he recognized was that to match a extremely conducting thin sheet to free space it was quite a challenge and required a resonant geometry using an interaction with a back reflector positioned with a thin sheet, in our case graphene, positioned a quarter of a wavelength in the index away from a back reflecting substrate. And the substrate imparts a pi phase shift, of course, upon reflection, and that leads to then an extinction of the reflected beam. And of course, with a back reflector, that means that leads to a condition for extremely high resonant absorption in this so-called Salisbury screen environment. And as we can tune the carrier density of graphene, this is a structure that is designed on a thin membrane. The dielectric material here is silicon nitride, which is chosen in thickness to be exactly a quarter of wavelength in the silicon nitride, separated from the graphene resonators. So essentially what we're doing is coupling this ensemble of graphene resonators to the external reflector. And when we vary the carrier density to tune through the graphene resonance, we can see that the absorption rises from the 2.3% value characteristic of single pass transmission to strongly resonant transmission here as high as almost as high as 25%. So we can tune entirely through this line width and see a significant increase in the interaction with even a single monolayer of graphene. And a way to think about this is that essentially what we're doing is impedance or admittance matching the graphene to free space. This was the insight that was first recognized by Salisbury. And we can, of course, view the resonators as having a real and complex part of their susceptibility or admittance. And essentially what we can do, because the whole structure is deeply sub-wavelength in dimensions, here the mid-infrared wavelength here is 7 microns, and the whole structure here is about a micron thick. So then we can essentially form an effective surface admittance that contains a component that's characteristic of a highly conducting surface and a tunable component. And then in order to obtain a zero reflectivity condition, we're going to essentially zero the numerator, which is this 1 minus admittance, and a factor, this coupling factor, which is proportional to the properties of the substrate. So I showed you just a moment ago an array of graphene resonators here sitting on a back reflector, the so-called Salisbury screen environment. We can actually further enhance this interaction by coupling the graphene resonators now to a plasmonic slit array in a noble metal structure. So now what we've done is to make a periodic array of metal slits and interpose graphene resonant ribbons within the slits. And so we can either position the ribbons to be exactly within the slits or asymmetrically placed with an even narrower slit. And what we can see then by using, and the electrical engineers in the audience will recognize that we can use a simple sort of Smith chart analysis to, in which this substrate coupling factor represents a tuning parameter for the real part of the effective admittance, and allows us to identify the condition. Essentially, there's a critical mobility in the graphene that defines the conductance and therefore the real part of the admittance. And what we're really trying to do to maximize absorption is to maximize the is to match the conductance of the and the admittance to free space. And so, for a fixed set of properties, as we change the conductance by the mobility, we find that there's a critical point here where we impedance match and expect to get to unity absorption. And what we found actually was that this kind of structure where we couple graphene nanoresonator ribbons to the slit arrays allows for a much better ability to match the impedance of the graphene for the mobilities of graphene that are accessible in these kinds of experiments. The mobilities are rather low after you go through this in the few hundred centimeters squared per volt second range as you go through all of the processing required to make resonant structures. And so indeed what we saw was that this allows one to raise the absorbance of a single monolayer of graphene as high as 70%. So we're getting very close to the unity absorption. This is something that's been sort of a holy grail among the people in this field for some time. And this careful matching of surface admittance allows us to get very close to this number. So that represents here. And as we change the Fermi level, you can see here, this is the absorption modulation efficiency and the actual absorbance itself here, which is changing from about 25% up to 70% as we change the graphene Fermi level position. So we can see very, very strong modulation of the absorption properties of even a single monolayer of graphene if we appropriately tune the admittance. So speaking of reciprocity, in these structures, unlike the nice, beautiful structures that Andreas showed, these are indeed reciprocal structures. So we expect by reciprocity inherent in the Kirchhoff radiation law that the absorptivity of layers of graphene should be proportional to the emissivity. And indeed, that means that we can tune by essentially now heating up and allowing these structures to become emitters. We can electronically tune the emission of graphene. And we've shown recently that we can see this, that we see a tunable emittance, electronically tunable emittance. And as a sanity check that this is not just a sort of background blackbody emission, we can see that it's quite polarization dependent, and we see emission only for the polarization characteristic of the electric dipole resonators of the graphene ribbons. So we can also see in other kinds of materials, for example, narrow bandgap semiconductors that form so-called topological insulator materials like bismuth antimony telluride, the optoelectronic properties that are quite interesting. And in topological insulators, as you may recall, the surface state that exists as a surface phase on a bulk insulator has a Dirac-like dispersion in which the electron spin is locked to the momentum and prevents backscattering of carriers. Backscattering is strongly suppressed and protected by time reversal symmetry. And so this is expected to lead to some very interesting structures that have not yet been observed, like the spin charge plasmon. So it's quite interesting to think about whether we can tune the properties of these materials. And typically, in the growth of materials, we've grown materials here together with the Shui group at Tsinghua University. The position of the Fermi level is tuned by changing the band gap and the doping, by changing the composition in bismuth antimony telluride thin films. You can see here in an angle resolved photo emission the indications of the Dirac-like surface state that lies above the bulk valence band in this material. And in thin film experiments, we can now look using infrared spectroscopy at the optoelectronic properties of gated thin films of these conducting oxide materials. And these are materials that are now peeled off their growth substrates as thin films of bismuth antimony telluride that have a bulk insulating state and a topological surface state on the top and the bottom. And the permittivity consists of contributions coming from the interband and the interband contributions of the topological surface state and the interband contributions of the bulk insulating state. And if we look at the infrared optical response, we can see as a function of gate bias evidence of tuning the Fermi level from the Dirac surface cone into the bulk valence band, and a simple model that accounts for the polyblocking and band filling that occurs as you deplete the surface state and then the bulk band upon excursion of the Fermi level is nicely in accord with these far infrared experiments. And you can see if we combine this with electrical measurements, transport and Hall effect measurements, we can see evidence that we're electrostatically able to tune the Fermi level from a position where it lies within the Dirac cone into the bulk valence band of the semiconductor. And these bismuth antimony telluride materials have the interesting property not only of being topological insulators, but also of being very efficient thermoelectric materials. And so by making an array of resonantly excited thermoelectric nanowires, we form an array of so-called guided mode resonant structures, where a periodic array of nanowires couples to a dielectric waveguide mode. It's possible to achieve extremely narrowband resonances and resonantly absorb the energy, incident optical energy, very efficiently in a very low heat capacity environment of a freestanding membrane with thermoelectric nanowires, either wired in parallel or to build voltage in a series thermopile configuration. So the Seebeck coefficient for bismuth antimony telluride, which is essentially essential to the figure of merit, ZT, and the thermoelectric efficiency, is particularly high for this material. So we can see that, in fact, in the guided mode resonance structure, full wave simulations show a resonant temperature rise that is directly in accord with the resonant absorption. So essentially what we're able to do now is to make a material that serves as a thermoelectric detector, which is very, very broadband. This is unlike a semiconductor detector, which has a band gap cutoff. These detectors have essentially the same kind of sensitivity just because they're absorbing heat from the visible to the far infrared. And we can see this manifest as a localization of the and a temperature rise in which the resonant excitation of the thermoelectric wires itself lead to a change in temperature of the wires on and off resonance. And so by changing the properties of the periodicity and the line width, it's possible to have a lot of flexibility in tuning the properties of these guided mode resonance structures. Here's some experimental guided mode resonance structures. And by changing the wire periodicity, it's possible to access wavelengths for guided mode resonances that extend from the visible into the mid-IR. So this actually implies the possibility of building in a single integrated unit a hyperspectral detector, this same material, that would be sensitive all the way from visible to mid-infrared. And these resonantly excited guided mode resonance thermoelectric wires, you can see here a very nice correlation between the absorption and the detected voltage induced by the Seebeck effect, which is linear in the power. And because of the very low heat capacity of these nanoscale wires on a thin membrane, they have quite a fast time response in the range of a couple hundred microseconds. The responsivity is not nearly as high as that for a semiconductor detector, but it's acceptably high. Yeah, we've done quite a bit of detail in studying the spectral detectivity and noise properties that I don't have time to tell you about. But to another horizon for tunable complex index materials has been to look at the properties of materials that lie between conductors and semiconductors. And this leads us to consider a broad class of materials known as transparent conducting oxides. And this is an area that's been pioneered by the group of Sasha Boltaseva at Purdue University. And transparent conducting oxides which are sitting on the laptop screens in front of you and your cell phone displays and almost every flat display as the conductor, have carrier densities that are tunable in this very serendipitous range between 10 to the 19 and 10 to the 21 per cubic centimeter. You can see this just by your own eyeball spectroscopy. If we look at a film of indium tin oxide that's doped from 10 to the 19, 10 to the 20, 10 to the 21. You can see the color change due to the imaginary part of the complex index changing. These are simple Drude models fits for the real and imaginary part of the complex permittivity. And you can see here that indeed across the visible to near IR, this is exactly the carrier density range that leads to a change in permittivity from positive to negative. And so this will be expanded on in the presentation of Howard Lee later this morning. So we can now fashion a reflect array antenna in which whose magnetic dipole response has this characteristic reflectance dip and phase change. Normally in a passive reflect array antenna, there's a dielectric gap between the patch and the ground plane. What we're going to do now is to interpose and add this tunable dielectric material, tunable conducting oxide, in which the patch antenna itself forms the gate to tune the carrier density and the permittivity of the indium tin oxide and change its phase and amplitude response. And here's an array of antennas that are all electrically connected to form a tunable metasurface. And essentially what we're doing is changing the complex permittivity within an extremely small region underneath the patch antenna gate in the range of 1 to 2 nanometers. By choosing the background permittivity and the voltage, we can now tune the permittivity from positive to negative with small applied voltages across the gate in the near infrared. And this just shows an example of the structures that have been made, so we can actually see that this is a fairly integrated device structure. And this forms a 1D array of subwavelength antennas. And these antennas have resonant magnetic dipole resonances in the near the 1.5 micron regime in the telecommunications band, and this allows for a modulation of the reflectance of about 30% with a few volts applied bias. But importantly, this also allows us to change the phase. So this allows us to make an electrically tunable phase modulator. And as we change the carrier density and permittivity in the conducting oxide, that changes the phase response of the magnetic dipole antenna by about a pi phase shift. This is, we can measure from a simple measurement using Michelson interferometry. And indeed, this structure, which is very transistor-like in its form factor as a device, operates like a transistor and can operate at quite high frequencies. We have tested the devices up to a few tens of megahertz in our lab, but in principle, these should be operable even at gigahertz frequencies. And indeed, if we now bus the antennas together in groups of 3, then groups of 3 antennas actually act as a tunable phase object that's about wavelength in scale. And so if we now tune groups of 3 antennas in a periodic bias modulation with zero bias applied to the next group of 3, we can form essentially a switchable diffraction grating, where we expect the reflectance to go from a characteristic 0 order reflection to one that is dominated by plus and minus 1 order reflection. This is a simulated change in the phase and the scattering response as a function of angle and bias, and this is an experimental measurement. So this essentially tells us that we've made an electronically switchable diffraction grating. So it's the sort of a first piece of experimental evidence that we can tune the phase properties of these subwavelength antennas, which is the first building block to build a beam steering element. So I'll just leave my conclusions here for you and see that we've been able to tune the properties of metals over a modest range, but by lowering the carrier density, we can achieve very interesting resonant tunability, including the ability to actively tune the phase in metasurface antenna arrays. So thanks for your attention.
Thank you. Thank you very much, Harry, for the excellent talk. The paper is open for questions. Right there.
Yeah, okay, so that's a very, very interesting question. So the question was, as you change the real part of the permittivity, how much does the imaginary part change? So you can see that almost directly. ITO is actually a fairly good Drude metal. So you can see here, as we change the real part of the permittivity, we are in fact changing the imaginary part as well. So indeed, you can see that is evidenced by the color change. So there is some loss. And that loss means that we get a resonance minimum. So the loss actually in these patch antenna structures comes both from the metal structure and the ITO, but a large part of this loss. That's why this reflectance at the near zero or ENZ condition is relatively low, about 20% or so.
Sorry, can you achieve the same carrier density? I beg your pardon.
I'm sorry, can you repeat the question?
Yes. Yes, go ahead, please.
Can you achieve the same carrier density range by doping semiconductors? How far can you go?
Okay. So the so the question is, can you play the same sort of tricks with doped semiconductors? Indeed, you can. It's just that as my almost my first slide indicated, that now the relevant frequency range for doped semiconductors will be in the far infrared. So so if we were interested in doing phase modulation, we can in fact use something like a silicon MOS channel or something like that to change the complex permittivity in the far infrared. But if you want to do this at 1.5 microns for something like a LiDAR application, that was one of the things that was motivating our interest in the conducting oxides, is to be able to do phase tuning in the near infrared. Then you have to have higher carrier density. But this is a very general picture that is applicable at a wide range of frequencies.
So building on these questions, do you see a way forward to do this kind of phase modulation away from the epsilon near zero conditions?
Yeah, that's an interesting question. I guess maybe the implication of your question is, could we actually see strong modulation with perhaps lower loss? Yeah, so that's an interesting question. And I think that the ENZ is always going to be a yeah, let's see here. So so the question is, if the colors are not showing well, but this is now, this shaded band here is indication of the ENZ response of our materials, which is now coinciding with the reflectance dip of the magnetic dipole resonance of this patch antenna. We can work, for example, on and see here phase modulation, but you can see that the region where the phase shift is occurring, which is essentially a fundamental outcome of the coupling of the real and the imaginary part of the susceptibility of this structure, is now, of course, largest near resonance. With this kind of structure, I think the largest changes in phase, for example, are going to occur near the resonant absorption.
For the question, let's thank Harry one more time. Thank you. Thank you very much, Harry.